Okay, this is a walkthrough of what we did in class on writing electron configurations. I'm going to give you a little bit of background about the periodic table and how it relates to the addresses where we can find electrons. Alright, so the first thing you need to understand is a little bit of background about atomic theory and quantum mechanics. Originally, when we discussed locations of electrons, we thought of electrons as traveling in what we called orbits. In other words, if this is the nucleus and this was an orbit, we could predict at any given time the location and the direction and even the speed of that electron. And that would be sort of like how we know that, say, Earth is orbiting around the sun at a particular speed at any certain point of the year on any day. We know in relation to the sun where the Earth is, how fast it's going, and the direction that it's going. Alright, so what we discovered was that orbits really didn't work. It didn't explain the behavior of electrons. And so two different scientists really governed what we would today believe the quantum mechanical model of where we find electrons. So one was Heisenberg, and Heisenberg came up with what's called the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle basically says that it is not possible to know the location and the direction of an electron at the same time. That if you simply try to measure one, you actually will cause the other to change. And so we can't really know the orbit of an electron. We can't know its exact location and direction, speed, and all of that. What we can know is the probability of where it would likely be found. And that brings us to Schrödinger, who came up with an equation. And his equation came up with a set of variables that would explain all the possible addresses of where we could find electrons in an atom. It was a mathematical function problem, and then the function had several solutions. And those solutions represent all the possible locations that electrons can be found. Alright, so based on Schrödinger's equation, there were actually four variables. One variable is the energy that an orbital contains, and we call this the principal quantum number n. If you think about this in terms of what you already know about atoms, if this was our nucleus, you may have learned that electrons are found in energy levels or shells, and that's what n represents. So level n equals 1 is the one closest to the nucleus, and then n equals 2, and n equals 3, and these are basically what you've probably heard before are the energy levels. The second variable is the orbital shape. So we have the energy level of an electron, we have the shape of the orbital or the area where the electron is located, the orientation, and then finally the spin. Alright, so these are probably not going to make, particularly shape and orientation, are not going to make sense just yet, but they will. Let me talk really quick about spin. So here's the idea. In one particular orbital, think of an orbital as like a bedroom in an apartment, you can only have a maximum of 2 electrons. And those 2 electrons don't want to be next to each other, so they spin in opposite directions. So it's sort of like 2 people sharing a bedroom, and they want to be on opposite sides of the bed. And so this is showing an orbital, and we represent the electrons with little arrows, and this would represent an orbital showing 2 electrons with opposite spins. Okay, so we said that there's the principal quantum number, n, and this is sort of like the shell, or if we're going to go with the apartment analogy, this would be like the floor. So you've got an apartment, and it's got the first floor, and that's going to be level n equals 1, and then we're going to have level n equals 2, and level n equals 3. And it turns out that based on Schrödinger's equation, there's a certain number of electrons that can live on each floor, and it changes floor by floor. The formula to calculate this is 2n squared. In other words, on the first floor, 1 squared is 1 times 2 is 2. So exactly 2 electrons can live on the first floor. On the second floor, 2 squared is 4 times 2 is 8. 8 electrons can live on the second floor. Third floor, 3 times 3 is 9 times 2 is 18. So 18 electrons can live on the third floor. and so on. And so this tells us the maximum number of electrons that could be found in any particular quantum level. Now, it also turns out that on each floor, the orbitals can have different shapes. So the first shape is called S, and it's actually a sphere shape. On the first floor, there is an S orbital, and it's called 1s because it's on the first floor. And on the second floor, there's an S, and that's called 2s. And on the third floor, there's 3s. So on each floor, there's a single S orbital. Starting with the second floor, it turns out that there's an S orbital, but in addition, there's also a P orbital. The shape of the P is actually a dumbbell shape, and it represents 3 different ways that electrons can be traveling. So not only is P got a dumbbell shape, but it technically has there's 3 P orbitals, 3 different orientations that P can take. So think of a P as a 3-bedroom apartment. So on the second floor, there is a 2P. On the third floor, a third floor P. On the fourth floor, 4P, etc. Starting on the third floor, it turns out that there is another orbital shape called D. D is actually like a 5-bedroom apartment. And then F starts on the 4th floor, and it's a 7-bedroom apartment. So imagine that this is a very strange apartment building, and what you've got is this. On the first floor, you have just an S. On the second floor, you have a 2S and a 2P, a 3-bedroom. On the third floor, you have 3S, 3P, and also 3D, which is your 5-bedroom apartment. On the fourth floor, 4S, 4P, which is your 3-bedroom, 4D, which is your 5-bedroom, and additionally a 4F. And this would keep going. In theory, this would just keep going up and up and up. Each level would actually have one more apartment in it, and that would hold more bedrooms. Okay, so there are 3 rules about where electrons will be located in an atom. The first one is called the Aufbau principle, and it basically says that our electrons are going to fill the lowest energy levels first. Now, when we first start off, that's typically going to be the first floor of the apartment building. So in other words, if we were looking at hydrogen, which only has 1 electron, we would find that electron in hydrogen on the very first floor. Suppose instead we were talking about oxygen. Now oxygen has 8 electrons. So if we were going to figure out where those electrons would be, the first 2 electrons would be on the first floor. On level 1, apartment S, 2 electrons. The second 2 electrons would be on the second floor in 2S, and there's our other 2 electrons. That now accounts for 4 electrons. That means we need to account for 4 more. So in apartment 2P, we would find our other 4 electrons, 2P4. That gives us 4, 5, 6, 7, 8. And that would account for the 8 electrons in oxygen. Now, even though P holds 6 electrons, notice that since only 4 needed to be placed, oxygen in 2P would actually only hold 4 electrons, leaving some empty space. The second rule, Pauli exclusion principle, we already talked about. This is the one that says that electrons have to have opposite spins. So in the 1-bedroom apartment of S, you could only have 2 electrons. In P, which was a 3-bedroom apartment, you could actually have 6, 2 in each bedroom. Lastly, Hund's rule. Now this one goes back to what we just talked about with oxygen. Hund's rule says that if they're all living in the same apartment building, for example, in 2P, and there are 4 electrons, they will spread out equally. So if you only had 3, for example, in level 2P, they would be like this. You would not find them like this, where they're next to each other. They won't share a room unless they have to. In oxygen, there's 4, so we would look at it like that. first 3, and then the fourth one would go back and share. Alright, so the Afbel principle said that the electrons fill the levels in order of lowest energy. So the lowest energy is not necessarily the lowest floor. So this little diagram shows you the actual order that the electrons fill. So you would expect it, based on what we've talked about, you would expect it sort of to fill the first floor, then fill the second floor, then fill the third floor, and so on. What we've discovered actually happens is, yes, the first floor fills, and what we're going to do here, by the way, this is a little shortcut, we're going to follow the arrows. So the first thing that's going to fill is going to be 1s. You get to the end of the arrow, the next thing is going to be 2s, go to the next arrow, the back of it, then 2p, then 3s, and then notice next, beginning of the arrow, 3p, and then rather than filling 3d, which is what you would expect, just if you assumed that it fills by floor, it goes from 3p, and now it actually is going to fill 4s. It just takes less energy to fill 4s than it takes to fill 3d. So experimentally what we see is you have to follow the arrows as sort of a shortcut to show you the correct order they fill based on energy. So it's going to fill 3d, follow your arrow, the next thing that would fill would be 4p, then 5s, then 4d, 5p, 6s, next arrow, 4f, 5d, 6p, 7s, 5f, and so on. So this is going to be the order that the shells actually fill. So let's say we're going to do strontium. Strontium is number 38 on the periodic table. And I'm going to skip ahead a little bit. If we do 1s2, 2s2, 2p6, 3s2, 3p6, we're now up to 10. Add these. This is another 8. So now we're up to 18. We've got to get to 38. Instead of going to 3d, we actually fill 4s first. So it's going to be 4s2. We're up to 20 now. And then we're going to go back and fill 3d. So we're going to go 3d. It's going to fill all the way up to 10. So now we're up to 30. We need to fill 8 more. We just filled 3d. Therefore, the next thing that's going to fill is going to be 4p. So that's going to be 4p6. We're now up to 36. We need to fill 2 more. We're going to go where? Let's see. Go back up to our little arrows. After 4p, 5s. And there we go, 5s2. And this is going to be our electron configuration for strontium. Whoa. So let's say we were going to do one that had, let's say, 14 electrons. If we were going to fill whatever element has 14 electrons, we would do this. We would know that the first 2 electrons would be found in 1s. The next 2 electrons would be found in 2s. The next 6 end up in 2p. So far, that's 10 electrons. We know that there's a total of 14. Where does this go after 2p? It goes to 3s. 2 electrons can go there. We're now up to 12. The last 2 electrons will therefore go in 3p, which can hold up to 6, but in this case is only going to have 2. So that's how we would write an electron configuration for that particular element. Now, we can also draw what we call the orbital diagram. An orbital diagram is sort of a physical representation of the same thing. It looks like this. Here's 1s, and this is physically showing the 2 electrons with opposite spins in 1s. The next thing we said filled was 2s, also has 1 bedroom, and it would look like this. 2p has 3 bedrooms, and it's filled, so 1, 2, 3, 4, 5, 6. 3s was next. It has 2 electrons, and finally 3p. And when you draw 3p, it's really important we follow one last rule, and this is called Hund's rule. Hund's rule says, basically, that electrons don't want to be next to each other. So if you have, for example, a 3-bedroom apartment, these are all in the same apartment, same amount of energy, and you only have, like in this case, 2 electrons, the proper way to write it would be 1, 2. it would be incorrect to do it like this, because electrons want to be as far apart as possible within a single level. So we couldn't just take one of the S ones and move them up, but within a single apartment, if it's a 3-bedroom apartment, we're going to put our first 3 electrons into the 3 separate bedrooms. If it happened to have 4 electrons in P, we would go back and then start filling them in next to each other. And that's called Hund's rule. And you can see that physically when you're writing orbital diagrams, but you won't actually see it physically when you write out an electron configuration, because this doesn't actually show you a graphic representation of where the electrons are located. The periodic table is organized based on how these levels fill. For example, everything in the first column right here ends with S1. Everything in the second column ends with S2. This whole section ends in D1, D2, D3, all the way up to D10. In fact, this is actually called D block. Notice it's exactly 10 wide, which makes sense because D holds exactly 10 electrons. S was 2 wide because S actually holds exactly 2 electrons. This over here is called P block. It's 6 wide because P holds 6 electrons. And finally, this down here is F block, and since F holds 14, it's 14 wide. Everything in this one ends with F1. Everything here would end with 1, 2, 3, 4, 5, 6, 7, 8, so this would end with F8. This element right here must end with D3. This element here ends with P1, 2, 3, P4. Everything here, except for helium, ends with P6. So the periodic table is organized not only into blocks in which each thing in the same column has the same ending, but it's also organized in the exact order that the electrons fill. Here's what I mean. Remember our little order of filling? We had 1s, 1s2, then 2s1, 2s2. What comes next? 2p up to 2p6. Then 3s2, then 3p6, then 4s2, and if you remember, they didn't fill quite in order. After 4s2, it went back and filled 3d up to 10, then 4p6, then 5s2, then 4d10, then 5p6. In other words, the table's organized in the order that the electrons actually fill their shells. 3d doesn't come until after 4s. So let's practice writing an electron configuration. Suppose we were going to write the electron configuration for zinc. It's right here. It's number 30 in the table. Now, one thing you could do is you can remember what I just told you. If this is D block and everything here ends in D1 all the way up to D10, you pretty much already know zinc must end with D10. That must be the last thing that fills. But you can also do this. Here's our little way of remembering the order that they fill. On level 4, you have 4s, 4p, 4d, 4f, 5s, 5p, 5d. And this keeps going, but I'm not going to go any further. We fill in this order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and then we would be to 6s. Alright, so zinc has exactly 30 electrons. Here's what will happen. 1s2, 2s2, 2p6. That takes care of 10. Then 3s2, 3p6. That's another 8. We're up to 18. 4s2. That's going to be 20. and then back to 3D after 4s is 3D, and we said we are now up to 10 plus 8 plus 2. We're up to 20 electrons. Zinc we said was number 30, so 10 more electrons, and there's our 30 electrons. And this would be our entire electron configuration for zinc. If we were going to draw out the orbital diagram, it would take more space, but we could also do that. 1s would have 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 3s, 2 electrons, 3p, another 6, 4s has 2, and then 3d has 10. And this, a little sloppy, would be our orbital diagram for zinc. There are a couple of exceptions to the rules that we just discussed. Sometimes what we discover is that electrons are going to fill their shells, remember, in the order of what's the most stable. And it turns out that sometimes having a half full shell is more stable than having something that's partially full. Let me show you what I mean. If we go to chromium, you would expect chromium, if you recall really quickly, we would go, it would end with 4s2 and then go back and fill 3d4. Now, what happens here is D is almost half full. Well, it turns out that it actually ends up being a little more stable. It's one of those things sort of like in the English language we have rules, I before E, except after C. Okay, well, so here's the thing. What chromium's actually going to do is it's going to do this. It's going to fill 4s1, 3d5. What's now happened is D is exactly half full. And yes, now S isn't full, but S is also half full. And because both of these are half full, it turns out this is just what chromium actually does. And for the purposes of our class, even though this only happens sometimes, we could assume that anything in this column, again, we're making an assumption that's not always true, but just to keep it simple, that anything that ends with, let's say even 5s2, 4d4, like molybdenum, might do the same thing. End with 5s1, 4d5, giving this half full. Now another thing that we're going to see is actually the opposite, not the opposite, I'm sorry, is a similar thing that we're going to see with having a shell that's almost full. So if we take a look at this time, let's take a look at copper. So copper would be expected to end with 4s2, 3d9. Now this 9 is so close to being filled that what we've discovered copper really does, very similar, it's going to steal one from S, so that it actually is going to end with 4s1, 3d10. And so now S is half full, if we look at this, and that is at the expense of making S half full, we've made D, which is really big, completely full. And so again, for the purposes of our class, we're going to simplify, and we're just going to assume that anything in this column, even for example silver, which we would expect to end with 5s2, 4d9, we're going to assume it's going to also end with 5s1, 4d10. The last thing I want to show you is a shortcut. And this is how to write abbreviated electron configurations. Because all we're really going to care about after this chapter is going to be the valence electrons, which are your outermost electrons. For example, and you can actually see this by the order of the periodic table as well. If we think of, for example, these on the end, these are all our noble gases. The reason why they're called noble gases is because they're fairly unreactive, and the reason they're unreactive is because they all have their top floor filled. So in other words, helium, if you recall, the top floor, the first floor is, on the first floor we have 1s. Helium's full, it's 1s2. If we look at neon, our next one, it ends with 2s2, 2p6. So guess what? The second floor is full. If we go to our next one, argon ends with 3s2, 3p6. The third floor is full. Now you might say, wait, but I thought the third floor also had a 3d. That's true, but here's the thing. Remember, 3d doesn't fill, if we go by our arrows, until after 4s. So technically, even though 3d is on the third floor, by the time 3d starts filling, we're actually on the fourth floor. We've already filled some of the fourth floor, so our third floor is not our outermost floor anymore. And so same thing, if we go to krypton, krypton ends with 4s2, and then yes, 3d10 goes back and fills, but our top floor is 4s2, 4p6. Krypton has its top floor filled. Alright, so at this point, let me show you a couple of things about this. So, for example, calcium. So the top floor in calcium, 1, 2, 3, calcium's going to end with 4s2, and that's going to be its top floor. And so, since calcium ends with 4s2, we can represent the valence electrons, just looking at the outer ones, like this, with dots. And this is called a Lewis dot structure. Everything below that, we had 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Now, here's the thing. All of this is basically not the top floor. This represents, if we were to look at what element has this configuration, it would actually be argon, which is the noble gas that comes before calcium. So here's the thing. Shorthand electron configuration for calcium is we can say, hey, calcium looks just like argon underneath, but on the top floor it has 4s2. That's our abbreviated electron configuration, and it matches up with our Lewis dot structure. So let's look at another one. Let's look at bromine. Alright, so here's bromine. Now, if we find the noble gas that's closest to bromine, but smaller than it, that would sort of represent our core electrons. So if we go up here, we see that here's bromine, and the noble gas that's closest to it, without going over, would be, that would be argon right over here. And so if we go to write our electron configuration for bromine, we could say, well, bromine looks just like argon underneath, but what comes after argon, if we're going to now fill in the order of shells, next would be 4s2, and then, we'd go back and fill 3d10, and then we would fill 4p1, 2, 3, 4, 5, 4p5. This would be our abbreviated electron configuration. It looks just like argon, but these would be the things that would fill after argon. Now, if we were going to draw our dot structure for bromine, it ends with 4s2, 4p5. Why am I not including the 3d? Because 3d is not on the top floor that's just filled, it's actually on the floor beneath. So I'm going to ignore it for our dots. So this means that bromine has 7 dots. We would draw them like this. Going along with that whole thing about them not wanting to be next to each other, we start by doing that, and then we can fill in the other 3, 5, 6, 7. That's bromine, or you wouldn't have to do it that way. You could also do this. You could go 1, 2, 3, 4, 5, 6, 7. In other words, as long as you have 7 dots, and they're all paired up except for 1, that would be fine. If you were going to do it for carbon, let's take a look at carbon. So carbon's up here. Let me make another box here. Alright, so looking at carbon, if we were going to write its shorthand structure, we'd say, okay, so for carbon, I noticed that the noble gas closest to it is up there, helium. So carbon looks like helium, but then after helium is, this is starting to get really messy, 2s2, and then 2p2. How do I know this? Remember, if you go back a few slides, everything here ends in p1, p2, p3, p4, p5, etc. So this would be carbon. So this is our abbreviated electron configuration, and if we were going to draw the dots, carbon has how many in its outer shell? 2 and 2 makes 4, because our top floor is the second floor, and the proper way, they don't want to be next to each other, would look like this. So that would be the Lewis structure, showing the valence electrons for carbon. Let's do one more shorthand structure. Let's say we go all the way down here to barium. Alright, if we were going to write out the whole structure, we know that barium would look exactly like, all the way over here, oh, it would look like xenon. That's the noble gas that's closest to it. So that's going to represent our inner core electrons that wouldn't be reacting with anything. And then what would come after that? Well, we can count it up. 1, 2, 3, 4, 5, 6, 6s2. This would be our shorthand abbreviation. It looks just like xenon, but has 6s2. And if we were going to draw the dots, we would draw 2 dots. As long as they're not next to each other, you could draw that. Or you could do them like this. But you're basically showing it has 2 electrons in its outer shell. That's its valence shell. All right. Now, we could also do this. Let me draw yet another box here. I want to show you one other thing about this. Now here's the thing, remember, they all want to have 8 electrons in their outer shell. Why? Because all the noble gases have 8 in their outer shell. I showed you that a moment ago. So if we take a look at that, they want to have 8 in their outer shell. We can also notice one last thing about the table here, and that's this. If carbon, for example, well, let's do potassium. Potassium is in our first column. It has 1 in its outermost shell. Now, if it wants to have 8, there's 2 things it could do. If we were to write this whole thing out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This would be the whole thing. If we were going to do our shorthand, we would eliminate everything except our last one that filled. Potassium would look like argon with 4s1. So there's our dot, there's our shorthand abbreviation, and if it wanted to have 8 in its outer shell, it would either have to gain 7 more, and then it would look like krypton, or it could lose 1, and it would look like argon. In other words, it wants to look like one of the noble gases. What's going to be easier to do? It's going to be easier just to lose 1 than gain 7. So potassium, when it forms an ion, is always going to form a +1. You may say, wait, you just said it would lose 1. Why is it a +1? Because remember, electrons are negative. So if it loses an electron, it's going to get a +1 charge. Not only is potassium going to get a +1 charge, but every single one of these in the first column, everything in S1, is going to tend to get a +1 charge. All of them. And in our second column, they all end with S2. Again, they can either gain 6 or they could just lose 2. Either of those options would make them look like a noble gas. Well, obviously, it's going to be easier to lose 2. So everything in the second column is going to form a +2. We're going to ignore D block for now. They do some different things that we'll talk about. We're going to skip all the way over here to P block. So this one ended with P1, and they all had 3 electrons in their outer shell. Again, we could either gain 5 to look like the next noble gas, or we could lose 3 and look like the previous noble gas. It's going to be easier to lose 3, so everything in this column is going to tend to form a +3 charge. Now we get to the fourth column. Well, this is the carbon where carbon is. It could either lose 4 to look like the noble gas before it, or gain 4 to look like the next one. Well, that's sort of an exact halfway point, and what we're going to find is a lot of the things in this column aren't going to gain or lose. They're going to share. They're going to tend to form covalent bonds and share. Some of the ones near the bottom actually do tend to form a +4 charge. Okay, and now that we're past carbon, now we're actually getting closer to 8. So here, these all have 5 in their outer shell. Well, now we're going to see the opposite situation. Are we going to lose 5 and look like the noble gas before it, or are we going to gain 3 and look like the next noble gas? Well, in this case, it's now going to be easier to gain 3. So these are all going to tend to form a -3 charge. Again, why? If we look at nitrogen, it had 1, 2, 3, 4, 5 in its outer shell. Easier to gain 3 than lose 5. Electrons are negative. Gaining 3 means it's going to get a -3 charge. Now this is getting really messy, so let me just cover this up one more time. Alright, and so here's what your periodic table is going to look like when we look at what kind of ions they form. They're going to form +1. These are all going to form a +2. We're going to ignore these. These are all going to form a +3. These are going to tend to share, although a few down here will form a +4. Now we're getting closer to the other side. These all had 5. They're going to form a -3. These all have 6. They're going to form a -2 to get 8. These all have 7. Form a -1 to get 8. And these all have 8 already, so they are going to tend to not react. Except for helium. Helium doesn't have 8. It actually only has 2. But remember, the first floor, that is a full first floor. So that is kind of what we're going to be looking at in the chapters coming up. What kind of ions do they form? +1, +2, +3. These tend to share. -3, in other words, gain 3, gain 2, gain 1, and then they'll share. When they do that, they're either going to end up with 8 dots in their outer shell and look like the next noble gas, or lose their outer shell completely, in which case they're going to look like the previous noble gas. Alright, so I hope that's helpful. What we've covered is all of the rules about how electrons fill their shells. We've gone through how to write electron configurations. We've gone through how to write orbital diagrams. We've gone through exceptions to the rules, the ones that end up with half full S's in order to either give a half full or a completely full D. We've gone through abbreviated electron configurations. We've gone through how to write electron dots for the valence electrons. And finally, we've touched on what kind of ions these will form in order to get full outer shells. So that covers everything that's in the PowerPoint. Hopefully that's sort of summarized things for you and clarified any problems you were having.